Bismillahirrahmanirrahim. In this video, we'll explain example number 8.2 given in the chapter 8 of the book. Let's see. Example 8.2, a 50 HP, 250 volt, 1200 revolutions per minute DC shunt motor without compensating winding. Now let's stop here. What it is, this part is same as we had in example 8.1. So if you have not seen my previous video, I'll recommend that you first go and see that video so you are able to understand this part. But anyway, the point to emphasize here is that in the previous case, in example 8.1, it was with compensating winding. Here it is without compensating winding. And as I had explained in the previous video, that because of the movement or the rotation of the armature, there is a magnetomotive force produced which opposes the magnetomotive force produced by the field winding, and therefore there will be a loss of the magnetomotive force. And to compensate that, we put some kind of winding on the poles of the motor, and that compensates for the armature reaction. Now in this case, there is no compensating winding, so we'll see what is the effect of this. Okay, so shunt motor without compensating windings has an armature resistance including the brushes and interpoles of 0.06 ohm. So this is the armature resistance. Its field circuit has a resistance of 50 ohms. So this is the resistance of the field circuit, RF plus R adjustable, which produces a no load speed of 1200 RPM. So no load speed is 1200 RPM. Now for my ease, I prefer that the field windings are on the left hand side, so I have just redrawn this circuit. Now let's keep reading the question and try to understand. There are 1200 turns per pole on the shunt field winding. So the shunt field winding has 1200 turns per pole, and the armature reaction produces a demagnetizing magnetomotive force of 840 ampere turns. So now that the armature reaction is present, it is creating a force which is 840 ampere turns at a load current of 200 amperes. So this phenomena or this data 840 ampere turn is only for when the load current is 200 amperes. The magnetizing curve of this machine is shown in figure. So this is the magnetizing curve, which is the induced torque versus the speed. Now for the speed of this motor, find the speed of this motor, that is the first part. Find the speed of this motor when its input current is 200 amperes. Number 2, this motor is essentially identical to the one in example 8.1 except for absence of compensating winding. How does its speed compare to that of the previous motor at a load current of 200 amperes? So we want to see how does the speed vary in this and in the previous example. And finally, we need to calculate and plot the torque speed characteristics of the motor. Okay, so the first part, find the speed of this motor when the input current is 200 amperes. So IL, this current IL is 200 amperes. And from here we can find the armature current, which is IL is actually IA plus IF, and therefore IA is IL minus IF. IL minus IF is now again this voltage VT divided by this resistance. So Vt divided by the resistance. IL is 200 ampere minus Vt is 250, RF is 50. So the armature current becomes 195 ampere. And the internal generated voltage EA is Vt minus IARA, this voltage. This plus this is equal to Vt. So from here EA is Vt minus this voltage drop. So Vt minus IARA. Vt is 250, IA we know 150, 195, and RA is 0.06, this resistance here. So the induced voltage is 238.3 volt. Okay, the armature reaction produces a demagnetizing magnetomotive force of 840 amperes turns at a load current of 200 amperes. So this we have to keep in mind that this value, this force, is for only one current, 200 amperes. We'll discuss this later. But what is this magnetomotive force is doing is it is reducing the field current because it is opposing the original magnetomotive force. So the effect of this we can find is IF minus this force divided by NF. Now we know that force is equal to N into I, number of turns multiplied by current, or I is force divided by N. So this I, due to the armature reaction, is now the reaction force 840 divided by NF, the number of turns 12. And so original minus this will give the new IF, or the field current. So plugging in the values, now IF is 5 amperes. From here you can see originally this voltage is 250. This 250 is applied here, 250 divided by 50 will give you 5 amperes. So this current is 5 ampere originally, but now it is reduced by this factor. So 840 was the force divided by 1200 turns. So solving this we get the new field current to be 4.3 ampere. Now from the magnetizing curve, the effective field current would produce an internal generated voltage of 233 volt at a speed of 1200 rpm. So this is the magnetizing curve given for one particular current, 200 amperes current. And if we see this new field current 4.3, so from here we can see that the induced voltage is 233. So this is the new induced voltage, or we give it a name EAO. And now we can calculate the speed. We know this is the formula for a speed, one voltage by the new voltage divided by earlier speed and the new speed. And so from here we find the new speed is equal to EA divided by EAO. NO EA is 238.3 volt original. From the graph now we find 233 divided by the RPM 1200. So we get the new speed to be 1227 revolutions per minute. So now keep in mind that without the armature the speed the no load speed was 1200 revolutions per minute, but because of the armature reaction the speed has increased. Okay, now the second part, to compare between the speed of 8.1 and this 8.2. The motor essentially is identical to the one in example 8.1 except for absence of compensating windings. How does this speed compare to that of the previous motor at a load current of 200 amperes? So at 200 amperes, in example 1, the motor speed was 1144 revolutions per minute. So I have just copied from the 8.1, those who are interested. you can also follow this. So this was the speed that we got in 8.1, so 1144. And in this example, we saw that the speed is increased to 1227 revolutions per minute. Now notice that the speed of the motor with armature reaction is higher than the speed of the motor with no armature reaction. And why is this happening? So to understand this, the relative increase in speed is due to the flux weakening in the machine with the armature reaction. So the armature reaction is basically weakening the flux, or since it has reduced the magnetomotive force, original magnetomotive force, therefore the flux will reduce. And if we follow this equation, we had the induced voltage is equal to constant K multiplied by flux multiplied by speed. Earlier we had considered this to be constant because the field current was constant, but now field current is not constant, therefore flux is not constant and flux is decreasing, as we have mentioned here. So to keep the induced voltage equal, we have to increase the speed to balance it. So that is what is happening. That's when the flux is decreasing, the speed is increasing, and that is why we see the speed to be increased to 1227 revolutions per minute. And now the third part, calculate and plot the torque speed characteristics of this motor. Now to derive the torque speed characteristics of the motor, we must calculate the torque and speed for many different load conditions. So if you remember, in the previous example, we had calculated for different current loads, 100 ampere, 200 ampere, 300 ampere. We had found out these speeds, and then we had calculated the induced torque, and then we plotted the torque on one side and speed on the other side. So we need to have many different, for many different loads, we got to calculate these parameters. Unfortunately, the demagnetizing armature reaction magnetomotive force is only given for one condition, that is 200 ampere. So this was given, if you recall. The armature reaction produces a demagnetizing force of 840 ampere turns at a load current of 200 amperes. But we don't know how much will be the magnetomotive force when the current is, let's say, 100 ampere or 300 ampere or 400 ampere or 500 ampere, and therefore we cannot easily get this data. And so in the book, the author has taken the help of MATLAB to solve this part of the question. So those of you who are interested, they just follow the book. Thank you.